Hello, and thank you for attending our talk. This is Konstantinou, and I'm delighted to tell you about our work on detecting firmware modifications in embedded systems using hardware performance counters. This paper appeared in ICCAD in 2015. At that time, Terry Wang, the first author of the work, and I were PhD students at NYU. The other co-authors of this work are Maniatakos and Karri. First, let me start this presentation by providing a high-level overview of our paper concept. In this work, we have developed Confirm, a host-based verification tool that leverages existing hardware features to detect malicious modifications in embedded systems. Confirm is a low-cost technique to detect such malicious modification in the firmware of embedded systems by measuring the number of low-level hardware events that occur during the execution of the firmware. The key idea is that the execution of a program code in embedded systems can be characterized with the total occurrences of specified hardware events and the relationship between the occurrences of different monitor events. The execution of the valid path in a monitoring program code subroutine generates different vectors in terms of the occurrences of low-level hardware events. There are three key points I'll be discussing. We will first describe the technical details of our work, then present the paper's key contributions, and finally, we will discuss the long-term impact of the work as it was and is being extended and utilized by researchers and industry along several directions. To get started, let's look at the problem statement of our work in the context of embedded systems and how it addresses the literature gap when published. Embedded devices are an essential part of the connected world, used in a wide variety of applications such as simple home automation systems, mobile phones, and mission-critical industrial control systems. For instance, the digitization of smart grid control technologies leads to the formation of power systems substantially dependent on embedded devices. The data and programs written onto the non-volatile memory of an embedded device make the system functional as they connect hardware and software modules. All these necessary instructions consist the firmware layer of a system. As a result, firmware is a major focus for targeted attacks due to its substantial role in an embedded system operation. Effective security mechanisms are therefore of paramount importance in order to provide protection against malicious firmware attacks. The concept of exploiting vulnerabilities in firmware for malicious purposes has been reported in several studies. For instance, it has been shown in DEF CON 2011 how to completely reprogram a smart battery by modifying the firmware on it. In NDSS in 2013, it has been demonstrated that vulnerabilities in a printed firmware update mechanism can lead to arbitrary malware execution. Prior to our paper, numerous mechanisms have been proposed and implemented in order to detect malicious firmwares. Each implementation, however, requires either extra hardware components or verification methodologies which typically have significant impact on the resource-constrained embedded device in terms of computational resources, communication bandwidth, power consumption, memory usage, etc. Our work, Confirm, addresses the security issues of embedded devices without extra hardware components. Specifically, we address security concerns in embedded systems, taking into consideration their limited resources and reusing existing hardware and utilize the hardware features they support. Doing that, Confirm demonstrated that it can detect firmware modifications with low performance overhead, therefore providing a fair foundation from which to build security and trust in embedded devices. As I mentioned in the beginning, the key idea of Confirm is based on the observation that a program is composed of a sequence of various types of instructions which during execution can be seen as low-level hardware events, and the behavior of a program can be uniquely characterized by monitoring the total occurrences of those specified hardware events during its execution, as well as the relationship between the occurrences of different monitor events. These low-level hardware events are efficiently measured using hardware performance counters. HPCs are a set of special purpose registers that can count low-level hardware events, for example, clock cycles, instruction retirements, loads, stores, branches, etc. They are built in almost every legacy and modern microprocessor. For example, ARM9 has 6 counters that can count more than 70 events. In case of malicious firmware modifications, the occurrences of these executed hardware events will be different compared to legitimate firmware runs. Here we see an example of the blowfish encryption algorithm, which is a symmetric key block cipher. This is a firmware subroutine from an actual device, Cooperform6, a PowerPC-based recloser controller used in power grid applications. The valid execution includes 16 rounds. Therefore, if we modify the encryption rounds, this will weaken the cryptography and HPCs can be used towards detecting this modification. For example, the number of executed instructions will be different after the modification. This demonstrates that embedded systems are a great candidate for HPCs since they typically boot directly monolithic single-purpose software without loading an operating system, and the firmware tasks are executed in a single-threaded infinite loop. Therefore, HPCs can be used to profile and monitor for abnormal code execution. In summary, we utilize HPCs for security, which, although originally designed for performance debugging, they can be utilized for security purposes as they can provide application profiling by building HPC-based signatures. The high-level structure of confirm is shown in this slide. A legacy bootloader is extended with the confirm core. The core consists of three major components: an insertion module that places checkpoints in the monitor firmware, an HPC handler that drives the HPCs, and a database that stores valid HPC-based signatures. All these components are stored in write-protected non-volatile memory. This prevents attacks from compromising confirm while still allowing authorized updates on confirm when the monitor firmware needs to get updated. Once the execution reaches a checkpoint, confirm intercepts the control flow and redirects it to the core module. Specifically, the event counts for the previous check windows are read and compare with the corresponding signatures in the database. Our implementation uses an inline hooking mechanism for control flow interception and checkpoint insertion. The checkpoint insertion technique is shown in this slide. First, an instruction at a checkpoint is copied to a trampoline, which is certain memory location in RAM, in order to move the code around and verify its integrity. Second, it is being replaced with a jump instruction to transfer the control to the trampoline. In the third step, we jump back to the confirm core and jump back to the trampoline and execute the original instruction. At the end, we jump to the instruction after the checkpoint. With such an inline hooking, the functionality of the subroutine remains the same after applying the check. As for the detection, confirm uses a comparison-based two-phase detection scheme. In the offline profiling phase, the HPC signatures of all monitor execution paths are generated from a clean copy of the targeted firmware. In the online checking phase, the same monitor paths are measured and the runtime signatures are compared against the corresponding golden ones. The first version of Confirm was tested with two commercial firmware images. The embedded devices are a wireless access and access gateway embedded device, which supports an ARM Cortex-A15 microprocessor with 6 HPCs that can count 70 hardware events, and the recloser controller, a PowerPC-based embedded device with 4 HPCs that can count 40 hardware events. Because we wanted the extracted signatures to be repeatable and robust, we selected those events that are less frequent by the current unpredictable system state. Not all available hardware events are good candidates for modeling a repeatable signature, as the occurrences of some events depends on the system state. For such events, the occurrences vary dramatically given different executions. As extracted signatures must be repeatable and robust. Therefore, we executed a set of software modules multiple times on the same platform, and the repeatability was quantified with the coefficient of variation. A smaller coefficient of variation indicates a better repeatability of an HPC-based signature. The table in this slide lists the hardware events with the smallest coefficient of variation for ARM Cortex-A15 and the PowerPC platform. These events are the most robust, therefore are considered as good candidates for Confirm. To test Confirm, in the first platform we perform a denial of service modification attack. The attack targets the task scheduling module of the firmware. Specifically, we add a function hook to the check task switch subroutine to modify the normal control flow of the task scheduling algorithm. When a task with a specific ID is running, it will occupy the processor without being switched out, therefore it will impact the availability of other tasks. In the second platform, The recloser controller firmware modification includes a man-in-the-middle attack that performs Ethernet packet sniffing. Specifically, the attack targets the Ethernet packet receiving subroutine in order to capture the packets of data flowing across the Ethernet network. The modification intercepts the control flow in the subroutine and copies the received packets to a specific memory location. As a result, an attacker can retrieve the critical information in the received Ethernet packets. The HPC-based signature of the malicious path in both test cases exhibit deviations when compared with the signatures of the valid paths with the monitor subroutines. Essentially, the generated signatures are compared with the valid signatures included in the firmware check-in window to validate any matching occurrence and therefore demonstrating the detection capability of confirm with two actual firmware images and attacks. Overall, the technical contributions of our work are outlined in this slide. First, we designed a host-based validation tool that leverages existing hardware features to detect malicious modifications in embedded systems firmware. Embedded systems are a great candidate for repurposing existing hardware for security, since their firmware is executed in a single-threaded and infinite loop. Therefore, HPCs can be used to profile and monitor for abnormal code execution. In addition, our work presented the implementation of a prototype on an ARM and PowerPC-based embedded platforms, and the feasibility and detectability of the technique was demonstrated with two real-world firmwares and attacks. Finally, we also evaluated the performance and storage overhead when confirm was enabled. Historically, our paper was one of the early works of HPCs for system security, the first work to introduce HPCs for securing the firmware of embedded systems, both as a design for security concept and as an add-on feature, and the first contribution of evaluating an HPC-based security scheme or real-world firmware images used in embedded systems of critical infrastructure. Prior our ICCAD 2015 paper, hardware-based security solutions were not applied on embedded systems due to the overlooked security risk in embedded devices and high deployment cost for hardware modifications. The historical contributions presented in the previous slides can be confirmed by a recent 2019 Systemization of Knowledge paper appeared in IEEE Symposium on Security and Privacy. What we can observe here is that most of the security papers using HPCs were published after our work, and that our ICCAD 2015 confirmed paper was the first work of using HPCs for firmware security, as well as the first work of repurposing existing hardware in embedded systems for security. Now that we are aware of the technical and historical contributions and details of our work, let's discuss the potential of our work to have a long-term impact and why and how it influences other researchers and the industry. First, our work is driving and enabling the concept of HPC-based monitoring for safety and security of cyber-physical systems in multiple sectors. Following the publication of this paper, there has been a line of research on using HPCs for detecting security compromises and safety-related system failures in cyber-physical systems. For example, it has been demonstrated how to use HPC measurements to perform real-time monitoring of software running on embedded processors in cyber-physical systems. Also, it has been investigated the utility of multiple cores in embedded cyber-physical systems from the point of view of security, where one of the cores operates as a watchdog measuring metrics of HPC values. Furthermore, our work of repurposing HPCs for detecting malicious firmware modifications has inspired researchers to explore the feasibility of using HPCs for detecting advanced attacks such as return-oriented programming, ransomware, and side channels. Existing work in this area following our published paper includes leveraging HPCs to measure the mispredicted return events to detect rob attacks at runtime, or detecting microarchitectural side-channel attacks by profiling low-level hardware events using HPCs, which is demonstrating that HPCs can be utilized to detect different types of attacks. And given that attacks are evolving and becoming more sophisticated, there is a potential for improving HPC-based detection and prevention methods for new attacks. Moreover, the impact of work leads further research towards exploring the feasibility of using other existing hardware components for security. Our research on reusing readily built-in HPCs for security also triggers ideas of exploring other existing hardware components for security purposes. Modern computer systems, including embedded systems, nowadays provide various on-chip sensors to report real-time status of the system. Examples include thermal sensors and voltage frequency reporting interfaces. Similar to HPCs, these on-chip sensors readings may also correlate to the behavior of the programs running on the platform, therefore may have security implications. For example, Patel and others use thermal information to profile embedded processors to detect malicious changes due to software and hardware attacks and alter processors. While HPCs are a new channel for monitoring malicious behavior of a program, they also open an avenue for attackers to collect security-sensitive information. Concerns have been raised that HPCs might be abused as a security backdoor, and research efforts have been published along this line. In Usenix 2016, SPISAC introduced a hardware-assisted rootkit which allows an attacker to redirect control flow to malicious code by leveraging HPCs to count specific architectural events. In a more recent work, an adversarial sample predictor could determine the HPC count in order to get misclassified. In addition to the long-term impact of our work in regards to research and academic efforts, as well as the impact of our work on the research of utilizing HPCs in cyber-physical systems and other infrastructure sectors, our confirmed team and work paved the utilization of such hardware-based solutions in real-time industrial environments, showing that HPCs for security monitoring can be utilized in the next generation of embedded systems. Confirm was built by funding from Con Edison, a major electricity provider and one of the largest investor-owned energy companies in the United States. Based on confirmed success and practical demonstration, Con Edison and NYU received a $7.3 million award funding from DARPA to use and enhance confirmed capabilities towards protecting the US power grid and allow organizations that operate the power system to allocate their resources towards recovery, supporting government operations to investigate the attack without relying on immediate support from utilities and vendors. Furthermore, Confirm is used by other DARPA enforcement projects such as DARPA Sheath to safeguard against hidden effects and anomalous behavior. In this effort, Confirm is used in the identification and demonstration of real-time detection against malicious code installed in complex commercial off-the-shelf circuit boards. Now, let me briefly summarize the main points of this presentation. In this talk, we presented our Confirm paper, a low-cost technique to detect malicious modifications in the firmware of embedded systems by measuring the number of low-level hardware events that occur during execution. In order to count these events, Confirm leverages hardware performance counters which exist in many embedded processors. Overall, the benefits of Confirm include the fact that it resides in the boot ROM, therefore it is difficult to be detected or disabled by an adversary. Second, the monitoring can be instrumented within any firmware regardless of its functionality. And third, Confirm utilizes directly the lower level of abstraction in terms of hardware features of the host platform by passing the overhead associated with the software layers. Our work not only explored a new direction for hardware-based security solutions in embedded systems by reusing existing hardware features that were designed for other purposes, but also showed the practicality of such idea as the Confirm concept is expected to be used to protect critical infrastructures around the world, defending from malicious adversaries focused on disrupting critical system operations. That brings me to the end of my presentation. Thank you for your attention and thank you for listening. We'll be happy to answer questions during the live Q&A.